Oh, hello. Today's topic is another example of decimal to binary floating point representation and a discussion on imperfect binary representation. Oh. 89.42. We want to express this in a number system that is 1 bit for the sign and 5 bits for the exponent and 10 bits for the mantissa. All right. Yep, sure. Okay, so what I'm going to do is, first of all, note that is work out the mantissa, and to do that, I note that there's 10 bits, so I need to express 89.42 in binary to 10 bits. So I'm just going to worry about the integer part first. Let's turn 89 into binary, which is going to be a 64 plus 25. 25 can be a 16 and an 8 and a 1. So that's my 89 in binary. Now, how many bits does that use? That uses 3 bits. And so that gives me, that uses 7 bits. So that gives me 3 more to use because I'm allowed 10 total. So what comes next is the 0.42. I'm going to turn 0.42 into binary, double it, and I get 0.84. Double that, and I get 1.68. Double the 0.68 and I get 1 point something. It doesn't really matter what that's going to be because I've got my 3 bits, so I can stop there. So 0.11, that's as much accuracy as I can get on 89.42. You might be interested to know that's actually 0.5 plus. No, 0.25 plus. That's actually going to be storing 0.375. So we're not actually storing 89.42. We're actually storing 89.375, but that's as close to 89.42 as we can get using a 10-bit mantissa. All right, so we've got 89.4 whatever, 89 point as close as we can get, and that's going to be our mantissa. So if we're writing down our mantissa, it's going to be 10110011011. Now, my decimal point in a mantissa actually goes there. I'm just going to pause for a second. Can you just give me a moment? All right. So in this case, 89, if that's where our mantissa normally is, then we're making our number bigger. We want to move it 1, 2, 3, 4, 5, 6, 7 places. So if I'm going to move my mantissa 7 places, that means my exponent is going to be 7. And I just need to express that as binary. Remember that we're dealing with a 5-bit 2's complement number. So 5-bit 2's complement 7 is 00111. So that's going to be my exponent, 00111. And then this sign bit is our number positive or negative. All the way over here, I told you what we're actually converting is negative 89.42. So that's a 1 to make our number negative. That is negative 89.42 using floating point. Or as I said, it's as close as we can get. If we type that into a converter and actually find out what it is, we'll find out that it's negative 89.375. But that's as close as we can get with that system. You might be interested to note, I don't think does it say it in the notes? Let me just do a quick Google. Oh, have I crashed it?
It's kind of cool to see where the floating point inaccuracy actually comes from.
Yeah, I mean, most people don't know what the floating point inaccuracy is because we haven't talked about it much, but when we go back to our second Java unit, we're going to talk about how that impacts on the actual coding that we do. And so that 52 is obviously pretty massive. So, I mean, in our theory, we're talking about what happens when we're restricted to 10 bits of the mantissa, and that's the most accuracy we can get. But obviously, if we have 52 bits to the mantissa, we can get much, much more accurate than that. So we can get incredibly close to 0.3 to 89.42. But it's important to note as well, we still can't get there perfectly. It's still going to be a recurring decimal. We've got no way of restoring recurring decimals. We can just store them as 52 bits of getting close to it. And so that's why we've got a Java inaccuracy. Just to explain to others who might be paying attention at this stage what we're talking about with a Java inaccuracy, if you've got, let's say that in Java you've got a double, let's have two doubles, X and Y, and you might say let X equal, whoops, that and isn't very good Java, is it? Double X comma Y. Let's say X is equal to 0.2 and Y is equal to 10 divided by, no, I didn't want 10. I wanted 1 divided by 5. 1.0, because we want to make sure we're doing integer division. 1.0 divided by 5. Now on a calculator, 1.0 is divided by 5 is 0.2. But if I then say something like if X is equal to Y, then do some stuff, doesn't really matter what I'm doing. The point is that this isn't actually going to trigger. Mathematically, these two things are the same. X and Y are both 0.2, but you can't guarantee that this 0.2, sorry, you can't guarantee that this 0.2 is getting stored with exactly the same bit pattern as that. They will both be approximations of 0.2, but they might not be exactly the same approximations of 0.2.
Is Java like some languages where if they're close enough that double equals will trigger, or is that not?
No, you've got to code that in. Yep. So it's pretty standard A sort of question, might be testing. And how you do that is by saying if, and you'd say X, a better way of doing it is by saying something like,
you take the difference.
Yeah, take the difference, like X take Y, but we also want it to be the absolute value of the difference. So if absolute value of the difference is less than 0.001 or whatever you want your degree of accuracy to be, but that will just compare the difference between them, and then we can have our same code that will trigger if our numbers are incredibly close.